Good evening. Welcome back to the module Communication Theory, Learning Outcome 3. Actually, Unit 1 covered Learning Outcome 1 and the Learning Outcome 2. In Unit 1, we studied about the probability theory and random variables and its properties. After that, we studied about the random process and its properties and how to estimate the power spectrum of the random process. And then we studied about the filtering of the random signals. So in learning outcome 3, we are going to discuss about the what do you mean by noise component and what is the properties of the noise component, the effect of noise in the communication system, and then we are going to discuss about the filtering of the noisy signals. Noise. So basically, the noise is the unwanted waves, okay, which disturb the transmission and the processing of the signal in a communication systems. Okay, the basic sources of the noise, it may be to the external of the system or it may be internal to the system. Okay, so example for the external to the system, which generate the noise signals are atmospheric noise, galactic noise, and man-made noise. Coming to the second category, noise is coming from the internal to the system. Okay, so this kind of noise arises from the spontaneous fluctuation of the current or voltages in an electrical circuits, right? So this noise will make the basic limitation for on the transmission or detection of the signals in communication systems. There are two most common noise component which generate the from the internal of the system, okay, which is called short noise and thermal noise. So in this session, we are going to discuss in detail about what do you mean by short noise and thermal noise. So short noise. Short noise arises in an electronic devices. Okay, example diodes or transistors, which is coming due to the discrete nature of the current flow in an electronic devices. Right. For example, you can take the photodetector circuit. In that, the current pulse is generated every time when the electrons are emitted from the cathode. Right. When the incident light is occurring in the photodetector, then the electron will be emitted. So it is actually a random signal. It generates the short noise. The electrons are naturally emitted at a random times. Okay, from the photodetector, the electrons are naturally emitted at random times, which is denoted by tau k, where k varies from minus infinity to plus infinity. Okay, then the total current flow in the photodetector will be calculated by adding the infinite sum of current pulses. Okay, that is x of t equal to summation k varies from minus infinity to plus infinity h of t minus tau k, where h of t minus tau k is the current pulse generated at every time tau k. So this random process x of t is a stationary random process, and it also called as short noise. The total number of electrons emitted in the interval 0 to t is denoted by capital N of t. It is modeled as a discrete stochastic random process. And this count will be increased by 1 for every increment of electrons. Okay. The mean value of the number of electrons emitted between the interval t to t plus t naught is calculated. That is expectation of V equal to lambda t naught. That is the mean value of the number of electrons emitted in the time interval t to t plus t naught. So we can see from this equation where t naught indicates the duration where the electrons will be measured. Then the lambda indicates the constant and the rate of the process. The rate of the process means the number of electrons emitted per second. Rate of the process. Okay, we can measure the total number of electrons emitted in the interval t to t plus t naught by this mathematical expression b equal to the number of electrons emitted at a time t plus t naught minus the number of electrons emitted at a time t. Right? So the difference between the two time interval, the number of electrons emitted, which will be give the total number of electrons b. And this total number of electrons emitted at every time interval is a random nature, and it follows the Poisson distribution with the mean value equal to lambda t naught. So we can write the mathematical expression for the emission of electron at a time interval. Okay, t comma t plus t naught. That is, we can find out what is the probability for the k electrons emitted in the interval t to t plus t naught by using Poisson distribution. That is represented by probability of v equal to k equal to lambda t naught power k divided by k factorial into e power minus lambda k, where k varies from 0, 1 to up to infinity. So actually k is the number of electrons emitted at a particular time interval. So we can find out what is the first moment of the short noise, x of t. The first moment of the short noise is the mean value. So it is denoted by mu x equal to lambda integration minus infinity to plus infinity h of t dt, where h of t is the current pulse. So we have to integrate the current pulse over the interval minus infinity to plus infinity, and after integrating we are getting the mean value for the short noise. Similarly, we can find out what is the autocovariance of the short noise x of t, which is cx of tau equal to lambda integration minus infinity to plus infinity h of t plus tau into d tau. So this autocovariance of the short noise also called as Campbell's theorem. Okay. Now we can model the current pulse of the short noise as a rectangular waveform. Okay, rectangular waveform with the amplitude A and duration t. Then we can find out what is the mean and the autocovariance. Right. So the mean of the short noise process h of t. Now the integral limited from 0 to t. Okay, so the mu x equal to lambda integral 0 to t, the amplitude a into dt. By integrating, we are getting that mean value of the rectangular waveform h of t, which is equal to lambda at. Similarly, we can find out what is the autocovariance of the rectangular waveform h of t. Okay, that is cx of tau equal to same formula what we used in that the previous expression for to find out the autocovariance of the short noise. So here we are using that lambda integration minus infinity to plus infinity h of t into h of t plus tau into dt. So since the lambda is constant, we can take we can average the expectation of h of t into h of t plus tau, right? We can map this integration into this notation expectation of h of t into h of t plus tau. And since in that autocovariance there are two variables present, that is t, small t and tau. We can use that triangular function formula that we already studied in the previous session, right? Okay, because of the two random variable present t and tau. Okay, so we can take because the each current pulse it has the rectangular pulse has the amplitude a, so a squared we can take outside, so lambda a squared coming outside. Since there are two variable present t and tau, we can split the integral. So we can split the integral from minus t by 2 to plus t by 2 into two integrals. The first integral varies from minus t by 2 to tau minus tau plus t by 2. And the second integral varies from tau minus t by 2 to t by 2. So after integrating, we can get the t capital T plus tau plus capital T minus tau. Okay, and we can rewrite this expression as lambda a squared t minus modulus tau. So modulus means we can apply the minus tau and the plus tau. So this is the actually same expression like what we studied about the auto covariance of the triangular function, right? Okay, so that's the first type of noise component, that is the short noise. So the short noise is actually coming from the electronic devices, example, diode or transistor or photodetector. Due to that, the current fluctuation in the electronic devices. Okay. Next, we are going to discuss about the another type of noise component, that is thermal noise component. The thermal noise component is arising from the random motion of electron in a conductor, right? So that is the difference between the short noise and the thermal noise, right? In short noise, the short noise is arising in any electronic devices due to that the random fluctuation of electron, the random fluctuation of the current or voltages. Okay, that similarly in thermal noise arises in an okay, in a conductor due to the random motion of the electrons in a conductor. Right. So we can measure the parameter of the thermal noise. Okay, the first parameter, the mean square value of the thermal noise voltage, that is denoted by VTN. Okay, which is measured across the resistor. Right. So, for example, you can take the one of the conductor as a resistor, it's an electronic device. Okay, so in that resistor, it can generate the random motion of electrons whenever the current passes through the resistor. The random motion of electrons are occurring. So we can measure what is the mean square value of the thermal noise voltage. So which is the expectation of VTN squared equal to 4 T of del F. Okay. Unit is volts squared. Okay, where K is the Boltzmann constant and T is the absolute temperature and R is the resistance, unit is ohms, and del F is the bandwidth, unit is hertz. Okay, so for measuring thermal noise in this case we consider the simple resistors. Okay, so in that resistor there is a thermal noise is occurring, and we can draw the equivalent model for a resistor by using either Thevenin theorem or by using Norton theorem. So by using these two theorems, we can draw the equivalent circuit for the a noisy resistor, right? Then the equivalent circuit for the noisy resistor using Thevenin theorem, which consists of a noise voltage generator in series with a noiseless resistor, right? Similarly, by using Norton theorem, we can draw the equivalent circuit. That equivalent circuit, which consists of a noise current generated in parallel with a noiseless conductance. Okay, so conductance is the reciprocal of the resistance. Then we can find out what is the mean square value of the noise current generated, which is expectation of ITN squared. Okay, actually here the subscript is we have to change into a Norton theorem. Okay. So which is equal to 1 by R squared expectation of VTN squared, right? So by substituting that expectation of VTN squared, we are getting that the mean square value of the noise current generator, which is equal to 4 kTg del F, unit is amp squared, where G is the conductance. G equal to 1 by R is the conductance. So here the figure shows the equivalent circuit of the noisy resistor using Thevenin and Thevenin theorem and Norton theorem. The first diagram shows the Thevenin equivalent circuit for the noisy resistor. Okay, so which consists of the noise voltage generator in series with a noiseless resistor. In Norton equivalent circuit, there is a noise current generated in parallel with a noiseless conductor. Okay, this is the equivalent circuit for the resistor, noisy resistor. So that from that we can measure the what is the thermal noise. And from the resistor we can find out the maximum power of the thermal noise, okay, by using maximum power transfer theorem. Okay, as we know that the maximum power transfer theorem states that the maximum possible power is transferred from source resistance to the load resistance when the load resistance RL is equal to the source resistance R. If both resistance are equal, then the maximum power will be transferred across the circuit, right? Okay, so then by applying this maximum power transfer theorem to either Thevenin equivalent circuit or Norton equivalent circuit, we can find out what is the available noise power across the resistor. The formula for the maximum power in the across the resistor is using Thevenin theorem, which is equal to 1/4 expectation of Vtn squared by R. Okay, by after substituting the mean square value of noise voltage generator, that is expectation of Vtn squared. Finally, you are getting that available noise power across resistor equal to kT del of watts. Then coming to the third important types of noise is white noise. This white noise is mainly we are using that white noise in we are studying about white noise in communication systems, right? So it is customarily the noise analysis of communication system is customarily based on an idealized form of noise called white noise, right? Okay. Then the power spectral density of the white noise is independent of the operating frequency. That is a very important thing about the white noise. Okay, so it is independent of operating frequency component. Okay, so that is denoted by W of F equal to N naught by 2. Right, where N naught is the power of the white noise component, which is equal to K into TE. So the unit of the N naught equal to watts per hertz, and the TE is the equivalent noise temperature of the receiver. And second thing, why this noise we can call as a white noise? Actually, this is the noise which is occurring in the communication system, but it has some property which is matching with the visible light signal. That's why they are using that word white noise. So the adjective white is usually in the sense that the white light contain equal amount of all frequency component in the visible band. That's why they are using that word white in this noise present in the communication system. So which means that the white noise, it has the equal power to all the frequency component in the over entire bandwidth, which is varies from minus infinity to plus infinity. Okay, that the power is N naught by 2. So that's why we are calling the noise, this kind of noise in the communication system as a white noise. And another parameter is the equivalent noise temperature. Okay, so the equivalent noise temperature means a temperature at which a resistor is okay, we can connect the resistor to the input of the noiseless system. Then it produces the noisy power at the output of the system, right? Okay, again it repeat the equivalent noise temperature means, okay, at a temperature, okay, while connecting a resistor to the input of the noiseless noiseless system, then in the system produces the the available noise power at the output of the system. Okay, so this available noise power of the system is same as the other sources present in the actual system. Then the temperature is called equivalent noise temperature. Right? Okay, so here the waveform shows the power spectral density of the white noise. Okay, so it is a DC, it is a constant N naught by 2 over the frequency from minus infinity to plus infinity. That is the power spectrum of the white noise. It's a constant N naught by 2 over the range from minus infinity to plus infinity. It's a DC component, right? And the second waveform shows the autocorrelation function of the white noise component, right? It is an impulse function, it occurring at a tau equal to 0, the large amplitude, that is N naught by 2 del T. And how we are getting that autocorrelation function of the white noise means by taking inverse Fourier transform of the power spectral density of the white noise, right? Okay, so that is the notation for the autocorrelation function of the white noise is RW of tau, which is equal to inverse Fourier transform of SW of T, that is power spectral density of the white noise. We know that the power spectral density of the white noise is N naught by 2, it is a constant. And the second thing, the power spectral density of the white noise is constant, it varies from minus infinity to plus infinity. So it is since it is a DC component and also it is ranges from minus infinity to plus infinity, we can't directly find out the inverse Fourier transform of the white noise component, right? Uh, if you do that one, it becomes the infinity value because the ranges varies from minus infinity to plus infinity. But we know that the frequency component, for every frequency component, the magnitude, the power of the white noise is N naught by 2, right? So, so that we can get the autocorrelation function of the white noise occurring at the every impulse function, right? That is a del of tau. Okay. So the autocorrelation function of white noise consists of a del function weighted by the factor N naught by 2 and occurring at a delay tau equal to 0, right? And it is noted that the autocorrelation function is 0 at a tau not equal to 0, right? Okay. So here we can note down that the relation between the power spectral density and the autocorrelation function of the white noise. As I mentioned, we can't directly find out the inverse Fourier transform for the power spectral density of the white noise, right? It becomes infinity. So we can consider only one sample in the white noise. Okay, at one sample, say frequency f, the magnitude is N naught by 2. If you take the inverse Fourier transform of N naught by 2 at a frequency f, we are getting the impulse function, right? Because the Fourier transform of the impulse function again impulse function only, right? So that thus any two different samples of white noise, right? Any two different samples of white noise, okay, are uncorrelated to each other. So because we can said that the autocorrelation function is 0 at a tau not equal to 0. That's why any two sample functions are uncorrelated. Moreover, if the white noise is cos n, then we can say that these two samples are also statistically independent, right? And another important point about white noise, The bandwidth of the noise process, the input of the system is appreciably larger than that of the system itself. Then we can model the noise process as a white noise, which means that when the bandwidth of the input noise is larger than the system bandwidth, then we can model the noise is a white noise. Okay, so the white noise it has the bandwidth from minus infinity to plus infinity. So so we can't estimate we can't estimate the parameter like autocorrelation, and we can't predict the other parameter statistical information, so that we can go with the filtered white noise. Okay, which means by applying some filter, we can able to observe some other properties of the white noise. So for that, here we consider the one ideal low pass filter. Okay, so let us consider a white Gaussian noise omega W of t with a zero mean and the power spectral density n0 by 2 is applied to the low pass filter. Okay, which has the bandwidth B, right? And pass band amplitude response of 1. Then the power spectral density of the noise appearing at the filtered output. So the input we are applying the Gaussian noise omega t. At the output we are getting that N0T. Okay, N0T is the output noise. W of t is the input noise of the filter. Then the power spectral density of the output noise Sn of f equal to N0 by 2, but within the limited band from minus B to plus B and 0 otherwise, right? After filtering, the power spectral density of the white noise becomes N0 by 2, but it is limited to the band from minus B to plus B. Now we can find out the corresponding autocorrelation function for the filtered noise N0T. Okay, that is Rn of f equal to G minus B2 plus P N0 by 2 e power minus J2 pi f tau into df, which means that inverse Fourier transform of the power spectral density. We give the autocorrelation function because we know the relation between the autocorrelation function and the power spectral density. So the power spectral density will be calculated by taking Fourier transform of the autocorrelation function. But the autocorrelation function will be calculated by taking inverse Fourier transform of the power spectral density. That's why here we are applying the inverse Fourier transform, right? So, so the n0 by 2 is constant take outside. After integrating that exponential term, it becomes the e power j 2 pi beta minus e power minus j 2 pi b tau divided by j 2 pi tau. Okay. Then, okay. Now we know the formula for e power that exponential term e power j theta minus e power minus j theta divided by 2j. So this term we can write as a sine theta. So the autocorrelation function of the filtered white noise B n naught equal to B n naught into sine of 2 pi b tau divided by 2 pi b tau. So here, since in the numerator you can see there is a b, that's why we are multiplying both denominator and the numerator by b, right? To simplify this expression, we are multiplying both denominator and the numerator by b bandwidth. Okay. So now we can see here this is something like sine pi x by pi x. Okay. So sine 2 pi 2 b tau divided by pi 2 b tau, so which is equal to sinc function, sinc tau. So therefore we can rewrite this expression like as n naught b into sinc of 2b tau, right? So this is the autocorrelation function of the filtered white noise. Okay. So the figure shows, the first figure shows the power spectral density. It's a rectangular pulse. the bandwidth varies from minus rectangular spectrum. In the bandwidth varies from minus b to plus b. Then the magnitude is n naught by 2 for the range of minus b to plus b. Then the second waveform shows the corresponding autocorrelation function of the filtered white noise. It is a sync pulse, right? It varies from the x-axis is the time, tau, it is denoted by tau, and the y-axis is the magnitude of the autocorrelation function. The maximum magnitude occur at tau equal to 0, that is n naught into b. So this is the basic difference between the filtered white noise and unfiltered white noise. So the unfiltered white noise, it has the bandwidth from minus infinity to plus infinity. So in autocorrelation function, it has only impulse function. But whereas the filtered white noise, the power spectral density is a rectangular shape, rectangular spectrum, and the autocorrelation function is a sync pulse. And another important thing about the filtered white noise is the input noise omega t is a Gaussian, and the output noise n0t of the low pass filtered is also a Gaussian, right? After filtering also, the property does not change. Okay. The observation, the filtered white noise, let n of t is sampled at a rate of 2b times per second. Then the resulting noise samples are uncorrelated, and if it is Gaussian, then they are statistically independent, right? And the second thing, since the noise samples are uncorrelated, the joint probability density function of a set of noise samples, filtered noise samples, okay, is equal to the product of the individual probability density functions. Since the filtered white noise satisfying two conditions, it is uncorrelated and is statistically independent. And then each sample has the zero mean and the variance of n naught into b, where b is the bandwidth. Now consider the another type of filter, that is RC low pass filter. Okay, in that RC low pass filter, we can consider the input signal as a white noise, white Gaussian noise, say omega t, which has the zero mean and a power spectral density n naught by 2, right? Then the RC low pass filter has the transfer function in frequency domain, which is denoted by h of f equal to 1 by 1 plus j 2 pi frc, right? Okay, then we can find out what is the power spectral density, okay, appeared at the output of the low pass filter, okay. So which is denoted by Sn of f equal to n naught by 2 divided by 1 plus 2 pi frc whole square. So this is the power spectral density of the output noise. So the input noise is Gaussian, white Gaussian noise, that is omega of t. So that output noise is denoted by n of t, whose power spectral density is Sn of f equal to n naught by 2 divided by 1 plus 2 pi frc whole square. Then by you can use this Fourier transform pair formula, that is exponential of minus a tau equal to 2a divided by a squared plus 2 pi f whole squared, right? Both are reverse to each other, right? If you know this right side, we can easily find out what is the left side. So the autocorrelation function of the filtered white noise is calculated by taking inverse Fourier transform of the power spectral density of the filtered white noise Sn of f. Actually here subscript n, right? So now here we have to substitute that the power spectral density of the RC filtered white noise, that is n naught by 2 divided by 1 plus 2 pi f RC whole squared. Now we are going to rearrange this expression to apply this the Fourier transform pair formula. This we are going to convert it to exponential term, so that here we are rearranging the expression as 2RC divided by 1 plus 2 pi f whole squared into RC squared. Okay, since here we are multiplying with 2RC, but here there is no 2RC in the numerator. N naught by 2 is taken outside, so in numerator 1 is there. So for our convenience, we are multiplying both numerator and denominator by 2RC. So it becomes a 2RC by 1 plus 2 pi f whole squared, and this RC is taken separately, so RC whole squared, right? Then let A equal to 1 by RC. Then the autocorrelation function of the RC low pass filter the white noise equal to N naught by 4RC, the inverse Fourier transform of 2A by A squared plus 2A 2 pi f whole squared. After substituting A equal to 1 by RC, this expression will be rewritten as 2A by A squared plus 2 pi f whole squared. Now we can apply the formula of the Fourier transform pair formula. So we know 2A by A squared plus 2 pi f whole squared equal to exponential of minus 8 tau. So therefore we can write the autocorrelation function of the RC filtered white noise equal to N naught by 4 RC. Constant is coming as it is. Then this term is rewritten as exponential of minus 8 tau. Then we can substitute A equal to 1 by RC. Therefore, we are getting the autocorrelation function of the RC filtered white noise, which is equal to N naught by 4 RC into exponential of minus tau by RC. So here it is showing that circuit diagram for the RC low pass filter. It consists of the one resistor and a capacitor. Okay, it is connected in parallel. So the input is white noise, with your W of t. Output is again it is a white noise. It is denoted by N of t. So the waveform, first waveform shows the power spectral intensity of the RC filtered white noise, Sn of f. Okay, so it is limited in the bandwidth from minus 1 by 2 pi RC to plus 1 by 2 pi RC. It has the maximum magnitude of N naught by 2. Then this is the corresponding autocorrelation function waveform of this RC filtered white noise, Rn of tau. It has the maximum magnitude N naught by 4 RC. So from this expression, finally the magnitude is N naught by 4 RC for the autocorrelation function. So that here at tau equal to 0, it has the maximum magnitude N naught by 4 RC. And so in exercise, we are taking the interval as RC, 2RC, and so on. Okay, and this the maximum value going to be decreases to 1% at the value of 4.61 RC time value, right? So the observation. The decorrelation time tau naught of the autocorrelation function drops to 1% at a time 4.61 RC. If you take the reciprocal, it will give the sampling rate or the minimum sampling rate for the sampling of the white noise, right? So thus, if the filtered noise N of t is sampled at a rate equal to or less than 0.217 divided by RC. This 0.217 divided by RC is the reciprocal of this value, that is 4.61 RC. Then the resulting samples are essentially uncorrelated, and being Gaussian, then they are statistically independent. Right? Okay, that's it. So, so in this session we studied the basic types of noisy signals such as short noise and thermal noise and white noise. So mainly, particularly, we very much interested about the white noise because the white noise is studied in detail in the communication system to analyze the input received signal at the communication receiver. And this is that another topic. Actually, this is coming into the unit 1. a small topic that already we studied about the random variable. Then we need to know what is a Jacobian random variable, right? Because the scientist Jacobian derived that expression. That's why we are calling it a Jacob random variable. Okay, so consider the coin tossing experiment where the probability of it is p, and the probability of tail is 1 minus p. Let x be capital X be a random variable that takes the value 0. The result is tail, and 1 the result is head. Then we can say that the random variable capital X is a Bernoulli Jacobian Bernoulli random variable. So this is the mathematical expression for the probability mass function of a Bernoulli random variable. So which is denoted by P of x equal to capital X equal to x, which is equal to 1 minus P when x equal to 0. That is the result is 0. Result is tie. Result of the experiment is tie, and P and the result of the experiment is head 0 otherwise. You can find out what is the expected value of the Bernoulli random variable x. That is expectation of x equal to summation k varies from 0 to 1 k into p of x into x. So by putting k equal to 0, k equal to 1, we can expand this mean value expression. After substituting, we are getting that mean value of the Bernoulli random variable equal to p. Because k equal to 0 means the result of the experiment is tail. So tail means 0. K equal to 0 means 0 into 1 minus p, right? For x equal to 0, the p of x equal to 1 minus p. That's why here we are putting 1 minus p. Okay, when x equal to 1, the probability function is 1 p. So that here we are putting p. So 0 into 1 minus p equal to 0, 1 into p equal to p. So that the mean value of the Bernoulli random variable equal to p. Similarly, you can find out what is the variance of the Bernoulli random variable. We can use the same procedure for the variance calculation, but we need to find out the variance for the head and the tail. So that we can apply the summation k varies from 0 to 1. Then substitute the mean value and the corresponding probability function. Okay, finally we are getting the variance of the Bernoulli random variable equal to p into 1 minus p. That is denoted by sigma x squared. So now consider the set of independent Bernoulli random variable x1 to xn, right? It has the mean value p. Then the joint second moment will be calculated. That is expectation of xj into xk. If j not equal to k, then it's a product of x of j into x of k. If j equal to k, then it becomes x of j squared. So therefore, the joint second moment of the Bernoulli random variable, if j not equal to k means it will be p squared, because the mean value. So each one is the individual mean of the random variable, Bernoulli random variable. So expression of xj equal to p, xk also p. So p into p equal to p squared. But when j equal to k, it becomes p. So because expectation of j squared equal to summation k varies from 0 to 1, k squared into p of x into x equal to k. Okay, now we can expand the summation. Okay, by substituting the probability function, and it's the result of the experiment. So the first time will be 0. The second time is 1 squared into p, it becomes p. That's why when j equal to k, the second the joint second moment of the Bernoulli random equal to p. Thank you.